Singular value decomposition is a means by which we can understand how to factorize a matrix. And it has many useful applications, especially when you can't find an inverse of a matrix. You can use singular value decomposition to compute what's called a pseudo-inverse. You can do matrix approximation, and it's also extremely useful in all areas of science and statistics and things like signal processing and so forth. So as we said, it is a factorization of a matrix, and we can express any real matrix A in terms of its eigenvalues and eigenvectors. And so if we have A as an n by p matrix of rank k, then the singular value decomposition of A can be expressed in this form: A equals U matrix times D matrix times V transpose. And let's look at what those pieces are. So the D matrix is a matrix with entries on the diagonal as the eigenvalues of the matrix A. So if we have the eigenvalues of matrix A, that's going to compose our D matrix here, where the eigenvalues are on the diagonal. The U matrix is the matrix of eigenvectors of matrix A times A transpose. And the V matrix, or the V transpose matrix, is the transpose of that eigenvector matrix of A times A transpose. So this gives us our U, D, and V matrix. So here's an example of our singular value decomposition. We have our matrix A as 2, 1, 1, 2, and we compute our U matrix, and we compute our diagonal matrix and our V transpose matrix. And when we multiply these three matrices together, we can see that it will return our U dV. Now in R, we actually have a function in R to actually give us singular value decomposition, and that is SVD. And if we put SVD with our matrix A, we can see all the individual components. And using those components, we can recreate matrix A. And we can similarly do the same thing by hand, which we won't show here, but for another module.